Welcome to Narada Academy. In this video, we are going to discuss about equilibrium of three forces acting on a rigid body. So here I am going to give you only three results which play a very important role in solving the problems. The first one is for keeping a body in equilibrium under the action of three forces, the three forces must be coplanar. Okay, they must be coplanar. The second result is they must be either concurrent or all parallel. Okay, right, that is all the three forces must meet at a point or they must all be parallel. So this is the result which is very important for solving the problem. The another important result is trigonometric theorem. This theorem states, suppose if we have a triangle ABC and D is a point on the line BC, which divides it in the ratio m is to n. Okay, and AD makes an angle theta with the line BC, then m cot theta is equal to, m plus n cot theta equal to m cot alpha minus n cot beta. The second result is, when you don't know these two angle alpha and beta and these angles are known, angle BC are known, in that case m plus n cot theta equal to n cot B minus m cot C. Okay, so with these three results we are going to solve some problems. Let's see the first problem. Let me explain with the diagram. For these types of problem, the diagram is very important. With that only you can solve the problem. Okay, right. Let me see the problem. See here, a uniform rod of length A hangs against a smooth vertical wall, being supported by means of a string of length L. So first, let us take the first statement. We have a rod of length A. Let AB be a rod and let it be of length A, and it's a uniform rod they have given, no? So uniform rod means its center of gravity will be at its center. Let G be the center of the rod so that G divides a line in the ratio 1:1. Okay, it hangs against a smooth vertical wall. This is my wall, CD is my wall, and it is supported by means of a string of length L tied to one end of the rod, the other end of the string being attached to a point in the wall. So one string is there which is attached, one end is attached to the rod, the other end is attached to the wall, right? Okay, this is my string, BC is my string and it is of length L. Okay, right. Then what we have, other end of the string being attached to a point in the wall. Show that the rod can rest inclined to the wall at an angle theta. That is the inclination of the rod to the vertical wall is what is given, theta. And we have to prove cos square theta equal to L square minus A square by 3A square. Now let's come to the diagram in detail. So AB is the rod of length A and BC is the string of length L. Now here, what are the forces acting? Now first one is weight of the rod. Weight of the rod acting at G. Weight is always a downward force, so it is vertically downwards. Another one is the rod is touching the wall here, no? So you will be having reaction on the wall, which will be perpendicular to the wall. Okay, this is the reaction R, which is perpendicular to this one. Another one is the tension along the string, because it is tied to the rod, no? So tension will be created here. Okay, right. Now let us mark the angle. This angle I have taken as theta. If this angle is theta, this is the angle between the vertical line and the rod, no? So this angle will also be equal to theta. Okay, because this is also angle between the rod and the vertical line, no? So this will be theta. Right. If this is theta, this will be what? 180 minus theta. If this is 180 minus theta, this will be theta. Or if this is theta, this is also theta. Okay, right. So these two angles are known. Next one, this is alpha, no? This is alpha I have taken. Okay, for calculation purpose, I have taken the angle made by the string with the vertical line as alpha. So here also the same, because this is also the angle between the vertical line and the what string, no? So this will also be alpha, and this will be 90 degree because this is horizontal line and this is vertical line. Okay, so what is the concept I have used here? For keeping the body in equilibrium under the action of three coplanar forces, all the forces must be concurrent or parallel. Here parallel is not possible because weight is always a downward force, vertically downward force, and reaction here is horizontal, so they meet at a point. Therefore the third force, the tension, must also pass through the point of intersection of R and W. Okay, so all the three forces are concurrent. That is the result I have used. So after drawing the diagram, first you apply the trigonometric theorem. Okay, let me apply the trigonometric theorem. M plus n cot theta. So 1 plus 1 cot of, here instead of theta what we have, 180 minus theta, equal to 1 cot 90. This is 90, no? Minus 1 cot alpha. Right. So 2 into cot 180 minus theta is minus cot theta equal to This is 0, this is minus cot alpha. So 2 cot theta equal to cot alpha. So for problems of this type, draw the diagram and apply trigonometric theorem. Almost 90% of the problems will be over. After that, you look at the solution, what type of solution you need. Okay, after that, either you can apply Lami's theorem, triangle of forces, perpendicular triangle of forces, polygon of forces. Okay, uh, whichever is required there, you can apply, or simply you can use some trigonometrical results. Then you can obtain the answer. So for this problem, my aim is to remove this alpha, because this alpha I have introduced, this alpha I want to remove. So for removing this alpha, I am considering this bigger triangle BCD. Okay, from BCD, what is sine alpha? BD by BC. That is BD equal to L sine alpha. Again, you consider this small triangle ABD. Here sine theta equal to BD by AB. So BD equal to A sine theta. So for BD, I obtained two results. One is with alpha, another one is with theta. So equate them. L sin alpha equal to A sin theta, or sin alpha equal to A by L sin theta, or cosecant alpha equal to L by A sin theta. Right. So, but what is the standard result we know? 1 plus cot square alpha equal to cosecant square alpha, no? So in this one, let us substitute. Let us substitute. In one we know what is cot theta, and here we know what is cosecant alpha. So substitute the results. So what we have, 1 plus, instead of cot alpha, what I am substituting? 4 cot square theta. From using 1 and 2, in this result I am applying, equal to cot alpha. What is cot alpha? Cot alpha equal to L square by A square, cosecant square alpha. What is cosecant square alpha? L square by A square sin square theta. Right, understand? So here let us cross multiply. A square sin square theta plus 4A square sin square theta cot square theta equal to L square. So A square into, since the answer is given in terms of cos, let me change the sin square theta as 1 minus cos square theta plus 4A square, here sin square into cot square. What will happen? It is simply cos square theta equal to L square. So collect all the cos square theta terms. So 3A square cos square theta equal to L square minus A square, or simply cos square theta equal to L square minus A square by 3 square. So for this particular problem, I have used only the trigonometric theorem result and simple results based on triangles. Okay, so this is enough for this problem. Okay, right. Then next problem. A heavy uniform rod of length 2a rests partly within and partly outside a smooth hemispherical bowl of radius r. So consider a spherical bowl. This is hemispherical bowl. That's why only half portion I have drawn. The other half portion I have drawn in dotted lines, because I want full sphere for my calculation purpose. Okay, so this is a bowl. This part is the bowl, and we have a uniform rod of length 2a placed like this, like placing a spoon in a spherical bowl, no, in that same way they have. So this is a rod. AB is a rod and its length is 2a. Okay, so it's a uniform rod. So if G is the center of gravity, then AG equal to and GB equal to 2a, right? Okay, partly inside and partly outside, hemispherical bowl of radius r. What is the radius? Radius is equal to r, that is OA and OC are equal to r. Fixed with its rim horizontal, that is, this is the rim, no, this is horizontal. In that way it was placed. If alpha is the inclination of the rod to the horizontal, the inclination of the rod to the horizontal is alpha. So let me draw a horizontal line, dotted line I have drawn here, no, that is horizontal line. This is making an angle alpha here. Okay, right. What we have to prove is 2r cos 2 alpha equal to a cos alpha, and also calculate the reactions at the extremities. Now let's see what are the forces acting here. The first one is force. The first force here is weight W, which is acting vertically downwards. The other forces are the reaction. Here it is touching the bowl. No, here at this point and at this point you will be having reactions. So where will the reaction pass through? This is inside the this is inside the circumference. No, so it will be along the radius, along the diameter. Okay, so this is reaction RA, which is along the diameter from A. Okay, and from here this is on the boundary, no, so here the reaction will be perpendicular to the rod. Okay, so the reaction at C is RC. Since the three forces keep the body in equilibrium, all the three forces must meet at a point. So here let extend the W also, they all meet at the point D. Now let me calculate all the angles. See, this is alpha they have given, no, what is this? The angle between the horizontal line and the rod. This is alpha. Now see, here look at this one. This angle is 90 degree, because here it is always perpendicular, and this angle is also what, 90 degree. and this is r and this is also r, no? So the remaining two angles must be same because radius vectors, no? OA and OC is a radius vector, so this angle and this angle are alpha. And what about this angle? This angle is also equal to alpha, and this is 90 minus 2 alpha. How you are getting this as 90 minus 2 alpha? Look at this bigger triangle ACD. ACD is there, no? Here it is alpha, here it is 90. So what is the remaining angle? Remaining angle will be 90 minus alpha, right? And what about this angle? This angle is 90 minus alpha. How do we calculate this angle? Because here this is alpha, no? This is 90 degree, so this is 90 minus alpha. If this is 90 minus alpha, this is also 90 minus alpha, okay? And this angle is alpha, okay? So from the triangle we can find out all the angles. So after finding the angles, let me apply the trigonometric theorem first. So I know this angle and all the angles of the triangles I know. M plus n cot theta is equal to, here I am going to apply the result n cot b minus m cot c. The second result I am going to apply, because why I am applying this is, let me tell you. Here what is the ratio here? AG plus GC. Okay, AG plus GC into cot of 90 minus alpha equal to GC cot alpha minus AG cot 90. Though you know both the all the angles, why I am applying the second result means, here I am having cot 90, no? If cot 90 means what? That will be 0. Okay, so in order to get the result easily, I am applying. So whenever you have 90 degree, here you apply the second result, right? So AG plus GC is nothing but AC. AC tan alpha, cot of 90 is tan alpha. AC tan alpha is equal to GC cot alpha. This is my first result. Next, let me check whether I can use any theorems, named theorems, or simply some trigonometric results. Now look at the triangle ADC. ADC. In that triangle, what is sine of 90 minus alpha? That is, the total angle is 90 minus alpha, no? Sine of 90 minus alpha equal to AC by, opposite side is AC by hypotenuse. This is the hypotenuse, no? AD. That is 2R. So cos alpha equal to AC by 2R, or AC equal to simply 2R cos alpha. So AC I have obtained. Next one is GC I have to find. GC is nothing but AC minus AG. Okay, so GC equal to 2R cos alpha minus, what is AG? AG is nothing but half of the rod. The rod is of length 2A, so AG will be what? A, right? So 2R cos alpha minus A. Substitute these two values in equation number 1. So 2R cos alpha tan alpha equal to 2R cos alpha minus A into cot alpha, right? So 2R, here it will be sin alpha only. 2R sin alpha equal to 2R cos alpha minus A into cos alpha by sin alpha. So 2R sin square alpha equal to, that is this sin alpha. Let me take it to this side. So 2R sin square alpha equal to 2R cos square alpha minus A cos alpha. So 2R into, collect the cos square sin square terms here. Cos square alpha minus sin square alpha equal to A cos alpha. So 2R into, this is cos 2 alpha. Cos 2 alpha equal to A cos alpha. So the first result is proved. Next, what we have to prove is, we have to find the reaction at the extremities. That is RA and RC reactions we have to find. For that, I am going to apply Lami's theorem. So what is the statement of Lami's theorem? If three forces acting at a point are in equilibrium, then each force is proportional to sine of the angle between the other two forces. So that property I am going to make use of here. So how will I get? That is RA by angle between, sine of angle between W and RC is equal to RC by sine of angle between W and RA equal to W by sine of angle between RA and RC. So RA by, what is angle between W and RC? This is W and this is RC, no? So the angle is alpha. Alpha equal to RC by sine of angle between W and RA. W and RA is 90 minus 2 alpha equal to W by sine alpha, 90 minus alpha. RA and RC. RA and RC is this total angle, no? It will be 90 minus alpha. So RA by sin alpha equal to RC by cos 2 alpha equal to W by cos alpha, or simply RA equal to W sin alpha by cos alpha equal to W tan alpha, and RC equal to W cos 2 alpha by cos alpha. That's all. Thank you.